just equal to P12 minus P21. Okay, so what we're asking really is, are these off-diagonal elements the same? Another way of saying it, phrasing it. Okay, so this is sort of special 2x2 tables, right? So if I have bigger tables, those two things won't be the same. I'll say more about that in a second. So this hypothesis is sometimes written as P12 equals P21, and it's called hypothesis of symmetry, because these two things are equal, right? Now, what if I had a bigger table? If I have an I by I table, say I is equal to 4, and I look at marginal homogeneity, that is the proportion, there's 4, I put things into 4 categories, strongly agree, weakly disagree, whatever, right? There's 4 different categories: weak, strong approval, and weak, strong disapproval, say. And I want to know whether anything had changed. What I'm asking for marginal homogeneity is P1 plus equal to P plus 1 before and after? Is P2 plus equal to P plus 2 before and after? Is P3 plus equal to P plus 3 before and after? And is P4 plus equal to P plus 4? So I have 4 equalities that I would need to check, right? The symmetry would be the assumption that, well, P12 is equal to P21, P13 is equal to P31, P14 is equal to P41, P23 is equal to P32, P24 is equal to P42, and P34 is equal to P43. So what's the difference about these lists? This has how many equations? 4. This has 6, right? So as I goes up, this number will have I choose 2. This number will have I. So that suggests, and it's true, you sort of argue what we did over there, that symmetry implies marginal homogeneity, but not the other way around. This is a stronger assumption. So in 2x2 tables, they're identical, but for I by I tables, symmetry is a stronger assumption than homogeneity. So we could test these two things separately. Or another way of saying it is there's this hypothesis, and then inside of that is this hypothesis, nested hypothesis. This is the weaker one. That's the stronger one. Okay. But for 2x2, they're the same. So let's look at McNemar's test. So I have a table. So I'm interested in only these off-diagonal terms, so I can think of that as my n. And the null is P21 equals P12 is the null hypothesis. And under the null, this is just a binomial. So M12 or N21 are distributed binomial, N12 plus N21, and 1/2 as its parameter. That's what it means for them to be equal. In other words, it's just as likely that they went back and forth between those two categories. So we can use a normal approximation, and as you learned from the first couple of weeks, when this probability is right smack dab in the middle, the normal approximation for the binomial works pretty well. As long as n is bigger than 10 or so, normal approximation is actually pretty good. We get a test statistic, z, just n12 over n12 plus n21 minus 1/2, which is the expected. So that's our computed value. That's our expected value of the proportion. And this is square root of 1/2, 1 minus 1/2. This is the variance. So that's just n12 minus n21 over the square root of n12 plus n21. And that thing is distributed normal 0, 1 approximately. Okay. And it's a good approximation because p is so close to, well, p is equal to 1/2, which is where that works the best. So you could do z, normal 0, 1, or you can do z squared chi-squared with 1 degree of freedom. Or you could do an exact test as well, if you feel more comfortable with that. So plugging in the numbers from our example, z squared, so I just use the off-diagonal numbers, 150 minus 86 squared divided by 150 plus 86, 17.36. And z would be 64 over the square root of 150 plus 86, which is about 4.16. So you may not remember your chi-squared table, but you remember your normal 0, 1. So this is 4 standard deviations away, so this is very significant. This will give you the same answer. So p is very, very close to 0. So we feel very confident that the president's approval rating has fallen after this event. Okay, so this is one example where this difference of proportions makes a lot of sense. That's how we usually report approval ratings. But the one other wrinkle that you usually see in approval ratings is someone will say, they'll say, it's fallen by 4% with a margin of error plus minus, say, 2% or something, right? So that means what we're doing is constructing a 95% confidence interval for the difference of proportions. And for that, we just need to compute the variance of our statistic for difference of proportions. So our d is p12 minus p21. Our d hat is n12 n minus n21 over n. And assuming the sample is big enough, we think this is going to be normal with true, whatever the true value of the drop is. This is true change in approval, like 4% or whatever. And the variance of that amount. So that's big sample. Why don't I take a big poll? And the variance of d hat is 1 over n. It's in the notes. P12, 1 minus P12 plus P21, 1 minus P21 plus 2 P12, P21. And we, of course, don't have access to that true variance. What we need is an estimated variance from the data itself. And that will be n12 over n, 1 minus n12 over n, plus n21. So this is just a plug-in estimate, plus 2 n12, n21 over n squared. Okay, so that variance gives us our confidence interval. Here we have a point estimate, we have a variance, and we know the distribution. So we get a confidence interval more easily computed from the normal variant. And our confidence interval is d, plus minus 1.96, 95% confidence interval. 1.96 times this number, square root of v hat of d hat. And this works out to be the interval 0.021, 0.059. So this is 4%. The headline is 4% plus minus 2%. So that a confidence interval doesn't contain 0. So we think it's significant, which is consistent with this conclusion. So we can say in our, report that your approval rating has fallen by 4%, plus or minus 2%. So now you're just 1,600 phone calls from being a pollster. Okay, so again, to revisit the sort of what's the point? In other words, what's the gain of power? So what would be the wrong thing to do here? The wrong thing to do would be to forget that we had called the same person twice. Right? So what if we didn't know that, and we looked at the data, and we just thought, okay, this was a cross-section. They called 1,600 people at random at time one. They called a different, potentially, with replacement, they called another 1,600 people at random the second time. And we got exactly the same numbers. So what would exactly the same numbers be? Well, the truth, the table we had was this. 794, they kept approving. 570 changed their opinion. 150 went from approving to disapproving. And 86 went the other way. And the totals were 944, 656, 880, 720. So these totals become the data if we don't know what happened. Right? So if we think about it as happening the other way, with two cross sections, I have a time one and a time two, and I'm calling two, completely separate independent groups. At time one, a total of 944 people approved and 656 disapproved. And there were 1,600 in the sample. At time two, 880 approved and 720 disapproved, and there were 1,600 in the sample. And we're thinking of these as being different samples of size 1,600. And these have some totals too, right? So these totals are 1,824 and 1,376. So what happens is that this 880 goes there, the 720 goes there, the 944 goes there, and the 656 goes there. That's the wrong way to think about it, or a different experiment, depending on how you think about it. So what is our gain from using the same people twice? That's the change in power of these two different interpretations. So in this table, it really is just a test for independence, right? And this is not going to be such a wild number. This times this divided by that times that. Right? So if we just do a test for independence, in this table, that is the correct thing to do. We still get, the marginal hasn't changed. These ratios haven't changed, so we still get an estimated approval drop of 4%. But what has changed, so that's 944 divided by 1,600 minus 880 divided by 1,600. What has changed is the significance. So the Pearson chi-squared for this would only be 5.22. And that's directly comparable to this one. So okay, there's still a signal, but the signal is much, much weaker than it would have been if we compared the same people twice. We recognize that we had called the same people in both events. So there's another way of saying that the standard deviation of this thing goes up. We get a bigger confidence interval. Okay, so there's a huge gain in power between these two events. Okay, so the last topic, which I guess don't really have time to say, is this measure of agreement kappa. So the kappa is something where you have two raters